how to traverse a tree. By the way, if somebody is not able to hear, put it in the chat. I know that Chakravartikar already confirmed that he is able to hear me. Somebody is having difficulty, put it in the chat and then we'll try to solve your problem. Okay, Chakravartikar already gave a fantastic quote. I'm reusing the quote from a couple of classes ago because that was a class when not many people joined. Okay, but I want to reiterate again for the benefit of the students. Learning is not the product of teaching. Learning is a product of activity of the learners. That means a lot of hands-on experience. Okay, and one more time I'll reiterate the importance of interaction. I like this quote. I never used it before actually. He who asks is a fool for 5 minutes, but he who does not ask remains a fool forever. So the underlying theme there basically is asking questions is perfectly fine. Actually, even in a lot of my meetings at work, most of the time I don't understand what the other guy is saying. So I interject and say, sorry for asking a stupid question, but could you tell me what this is, what that is? So I never feel shy of asking questions. Okay. We'll see whether this will be a long class or it will be a short class today. I'll try to do the class slowly. The reason I'm saying that specifically is we covered trees extensively in the advanced data structures class. Chakravartikar knows that. The kind of depth that we go into trees there is amazing. All kinds of trees, AVL trees, B trees, n-ary trees, binary trees, pre-order traversal, post-order, in-order, all kinds of things. So I'll try not to race ahead, even though I'm tempted because it is such an exciting topic, right? And then the various types of algorithms to deal with trees. It's super exciting. But we'll try to go slow today. And some of these things, I could probably do it in some kind of random order too. It depends on how the lecture goes. But over the next few weeks, we'll come back to the same themes over and over again. So it's like I think of this as a quick breeze through, then we'll go over it again methodically. Okay. That's half the problem solved in a data structures class. It is that important. Okay. So, what is a tree? Okay, we'll begin with that. We'll begin there. Okay. So it's a finite, non-empty set of elements. So first there should be some elements. If it's all empty, there is nothing to do. Okay. And then in general, tree is a concept associated with a hierarchical data structure. Okay. Now what is a hierarchy? We'll talk about that too. Okay. Now when you have a hierarchy, we introduce concepts as a parent-child relationship. Okay. So we'll again look at the terminology there. Now why are trees important? Trees are all over the place. They are in nature and they are there in the business side of things, where when we have to draw an organizational structure, we use trees. File systems use trees. We know that from Windows. You are using Windows or Mac or whatever. You have file systems. The entire file system is designed based on a tree or a hierarchical structure. Entire programming environments have hierarchies. If you take networks, for example, the OSI reference model, we could call it a tree data structure based on a hierarchy. Okay? So we have trees all over the place. So there is no need to even justify why we need to use a tree. Tree is such a fundamental notion in computer science. So from a layman's perspective, we know what a tree is, right? It looks exactly like how it is being shown. Okay? So what do you have there in that image? You have a root. Okay. I do see JNTV students. Hi. Good. You can turn on your video if your network bandwidth is good. That's why I can see you guys and ask questions. Okay, great. So that's a tree, right? So what does a tree have? Let's put it in the chat, right? Even before showing slides, right? When you talk of a tree, what are the terms that come to your mind? Since I see the video of JNTV, you can put something in the chat for me, JNTV students. I don't see other videos. If others can, if they're ready to put. So what kind of terms that come to our mind when I look at a tree like that? So when you have it, you all have seen trees, you climb trees and all that. What are the things that are associated with a tree? Anyone other than Chakravarti Garu is allowed to answer. Is that a stupid question? What are the things most? Yeah, I think I should say that. What does a tree have? Okay. So Jntuk Kakanana, okay. Somebody is okay, perfect. Tree is a okay, very technical, very good. Tree is a non-linear data structure which is having head, no, oh my God. JNTV went too deep. Talk in terms of layman's language. That's good. You're right. Non-linear data structure. Agree. In the real life, got it. There you go. So somebody put leaves, roots. Okay? You have leaves, you have roots, and then you have somewhere in between the root and the leaf, there's something else. Branch, right? So we have a root. That's the root of the tree, you're seeing that. And then you have branches. And then you have leaves. Right? Okay, keep that in mind. Because there is nothing, we are not really inventing anything new. We use the same concepts here. Okay? Now, to JNTUV's point here, since we are computer scientists, we need to invent our own terminology. Okay? So we start using the terms such as nodes. Okay? So you have a root, okay, and then you have something called nodes, okay? And then you can start seeing some terminology building up here. There's a first node which is called the root node, okay? Each node has a variable number of references successors. So B, H, all of these things are successors. Okay? Each node other than the root has exactly one node pointing to it. If you see B, there is one thing going there. So there's some kind of a hierarchy. Now remember, it's a hierarchy. Is it a network? Is this tree a network? That might be a tough question maybe, I don't know, for second year students. If you notice one thing here, there is no circular loop. There is no loop anywhere here, right? From the root A going to the leaves at the bottom, there is no, for example, if I draw a line from B to A again, that becomes a network. That is a key difference between a network and a hierarchy. In a network, you can find a loop. In a hierarchy, you don't find a loop. Okay? 1 second. I want to check something here quickly. Okay. Okay, great. Let me go back to the presentation mode. We'll continue with the terminology. All nodes will have 0 or 1 more child nodes or children. Okay? 0 or more child nodes. Okay? So, here is a tree on the right. H is the root. It has a child called I. Okay? See how we are using different terminology? It's still roots, branches, and leaves. Okay? But in between, we are introducing some new computer science type of terminology here, right? So I is the child of H. Okay. And then I has 3 branches going. These arrows, you can call them as branches. Okay. So it has 3 children, as we say. So going from the bottom of this picture, you will see that J, K, and L are children of I, and I is the child of H. Now you'll also notice one more thing here. In the very first picture that I showed with respect to the regular tree in nature, the root was at the bottom and then it was branching out, right? The root is at the bottom, then you have the trunk, of course, and then you have branches, it's protruding upward. Whereas when we are handling this stuff in computer science and the way we do it, we always draw the tree with the root at the top. Okay, so it's exactly opposite of what we do in nature. Okay, the root is shown at the top, and from there the branches flow. You have intermediate nodes. I can call this I as intermediate node, and ultimately you come to the leaf level. Now, the moment you say leaf, what does it mean? Just looking at the picture, what kind of understanding you get from there? What kind of observations you can make from this picture? When I say J, K, and L are leaf nodes, what does it mean? Can anyone guess what it means? Based on the terminology that has been introduced here, we have nodes, we have children, we have leaves. So can you deduce something when I say something is a leaf here? In this case, J, K, and L are leaves. I know maybe it's a tough question. So when the moment you come to leaf, if you notice there is no other arrows going down from the leaf, because that is where the tree is terminating. After J, J does not have any children. A leaf node is signified by the fact that it does not have any descendants or children. There you go. Jntuk Moocs put it correctly. Nodes that do not have any children. Okay? So far so good. By the way, you will get to draw some trees in the class today, okay? Now, for those of you who have taken graph theory or some introduction to graphs and all that, you'll start seeing some graph-related terminology too. Okay? The degree of a node. Okay? So what is the degree of a node? It is defined as the number of its children. Okay? So in the case of I here, the degree is 3 because it has 3 children. Okay? Nodes with the same parent are siblings. Okay? Just like how you and your brother or your sister, you're all siblings of your dad, okay, or your mom. They're called siblings. Okay? Okay, let me go to the next slide. Okay? Nodes with degree 0 are also called leaf nodes. See how you want to seamlessly move from one terminology to the other one. Okay? So, it's a legitimate exam question, right? Draw a node with degree 0. Okay? Or draw a node with degree 1. You should be able to show graphically how I'm showing in the picture here. Okay? Now, between the root node and the leaf node, okay, root is A, and all these D, F, G, H, K, L, M, they are all leaf nodes. Between the root and the leaf nodes, there are some other nodes in between. Okay? They are called the internal nodes or intermediate nodes. I would not penalize you if you say intermediate nodes. If you say internal node, that is a much more correct term. Okay? So, you have a tree, you have a root node, and then you have some intermediate nodes, and then you have leaf nodes. Each node in a tree, you will have exactly one parent. If you notice here, there's only one arrow. If you look at B or H, exactly one parent, one line is there. from B to A. Okay? B does not have a second line from some other node, from the top. Okay? Unlike in real world where you have typically two parents for a child node, here we show only one. The only exception is the root node. Root node does not have anything coming into it. Okay? The degree of a node is determined by the number of children coming out of that node, right? So in the case of this picture here, the degree of L is 3, whereas the degree of E is 2, because there are only two nodes coming out of it, two branches. Okay? Okay. I just took some nice snapshot from somewhere here, some medical terminology here. I don't even know carnivora morpha. I have no clue what it means. Okay? Some kind of a zoology or something like that maybe. Right? You can see here, all the red things are marked here. They are the leaf nodes. Okay? Meaning there is no other branches going out of them. Okay? All the blue things that are marked here are the internal nodes. They are internal because there are still branches coming out of those nodes. Okay? Now here is an example of two trees that are drawn with these things called A, B, C, D, E, F. Okay? In our terminology, in computer science, we classify between what are known as unordered trees and ordered trees. Okay? So, that means when you have an unordered tree, how they are organized, it does not matter. Okay? So that means the order is not relevant. Where in the case of an ordered tree, okay, there is a specific criteria which we use to order the tree in a way. Okay? Then that ordering matters. Okay? That is what it is saying. Now when we get into representation of these things and implementation of trees to look at representing arithmetic expressions and so on, you will clearly see that order matters. Okay? So we learn a lot about ordered trees as we go along. Okay? Excuse me. Okay. So here is a shape of the rooted tree. Okay? So as you can see here, to go from A to F, okay? You can see how you can traverse from A to F, A to B, B to E, and F. Okay? So you can find the branches, how you traverse them and how to go from root to branch. Root via branch to the leaf node, there is a specific way. It's also called a path. Okay? The term that we use is a path through the tree, going from one node to another node. Okay. So what is a path? Path is a sequence of nodes going from A0 to AN. Terminology there. AK plus 1 is a child of AK. Okay. The length of the path. The length of the path is N, going from A0 to AN. Because numbering starts from A0, right? So in the case of BEG here, if you look at it, the path BEG, what is the length of the path? It is, you see the number of edges that are traversed, right? That is 2. Length is going from B to E is one edge, going from B to G is another edge. So you add them up, then the path is 2. Okay? Okay? Okay, somebody mute yourself, somebody has started the audio. Let me check. Otherwise I have to stop sharing and then mute you and then after. Let me check. Bolisati is not. Pragati SVCW. They came online. Let me mute your VCW. Pragati, I'm muting you. Okay, I've muted all of you now. Okay, good. So, you can see here the path, and then I'm showing some representation for what the path is going from a certain node to another node. Okay. So for each node in a tree, there exists a unique path from root node to that node. When we say unique path, what it basically means is there is only one and only one path. Okay. Notice that very carefully here. If it is a network, that means there's some kind of a loop. You could have several paths potentially. Whereas when you have a hierarchy drawn like this, you'll only have one and only one path. If this is a math course, I will show you how to prove that. But luckily, this is not a math class. Okay. Now, this length of this path is called the depth of the node. Okay. Going at a leisurely pace. I know you have just finished all of your internal exams. You must be thinking, instead of being in a class here, you would rather be in a movie theater somewhere, right? Munching popcorn and watching nice movie. You can't help it, right? You have to cover the material. So what is the length of the path here? Is the depth of the node. So when you talk about E is at a depth of 2 because the length is going from root to E is 2 edges, that is 2. Now if you take L here, how many edges are traversing? 1, 2, 3. Okay? The depth of the node is 3. Okay? Now interesting question comes up when you look at a tree like this. We talked about depth of the node, but what about depth of the tree itself? If I were to ask you what is the depth of the tree, what would be your answer? In this slide, we are only talking about depth of a node. But if the same slide is shown, I say what is the depth of tree, what would be the answer? I didn't define what depth of the tree is yet, remember? But some of you have taken some graph theory anywhere, you would know that. Faculty members are welcome to put the answer too. Okay, no one yet, okay. I'll continue since I did not give an answer yet. Okay. Now I'm introducing another term called height of a tree. Okay. The depth of a tree is also known as height of the tree. The height of a tree is defined as the maximum depth of any node within the tree. So if some node has a depth of 2 and some other node has a depth of 3, then the height of the tree in that case would be 3. Okay. Now the height of a tree with one node is 0 because that is a root. Okay, just the root node. Now just like in stack, when we wanted to keep track of empty stack with a -1 on the first element being on the stack being -1, we do something similar here. For convenience, we define height of an empty tree to be -1. Okay. Still chat here. Okay. I can't see any videos, so I'm assuming you're still following and it's all piece of cake for you. Here is an example from that medical or zoology literature, right? You can see here the height of the tree here, going from the top to bottom, is 17. So how do you get that? Basically, you have to, can you imagine, how do you write a program to determine the height of a tree? It's an interesting question, right? I'm assuming you are thinking now algorithmically. Okay? So if I give you a program call, okay, here is a tree, programmatically tell me what is the height of the tree. How do you start writing a program? Very interesting algorithm actually. Okay? Obviously you don't have the skill set yet, But hopefully by end of the term, you will be able to write a program to figure out the height of the tree. Okay. So here you start counting edges, right? Look at it this way, right? Manually, forget about how we do programmatically. How about we spend a little bit of time to figure out how to determine the height of this tree? What are some ways you will do it? Explain to me in some normal common sense terms. How would we determine the height of this tree? I said it's already 17, so but how are we determining that? Let's have some discussion here. Faculty members are welcome to pitch in too. I'm simply saying, how do I determine that? Even looking at it on a piece of paper, right? Is there some way of optimizing that stuff quickly? I want some answers. But there is no right or wrong answer. Even I may not know what the right answer is, at least today. Even I have written programs to determine these things as a faculty member and as a student too. So obviously we started the root node, right? So you look at the root node, and I'll probably have some kind of a for loop maybe. Forget recursion for now. Somewhere recursion comes to. And then the root node, and let's assume for the sake of argument, it is a binary tree. I think this is a binary tree. Yeah, it is a binary tree. What is a binary tree? I just use the word binary tree, students. Binary tree means basically it has two branches. Every node would have at most two branches. I'm not being very technical here. Faculty members, don't jump on me because I'm not defining it 100% accurately yet. I think it's basically at most two branches. Okay? So if it has one branch all along, it is still a binary tree. The condition is at most. Okay? So this looks like a binary tree to me because every node has two branches coming out of it. Of course, leaf nodes would not have any branches coming out of it. It's not only a binary tree, I think it is we call it complete binary tree. Is it a complete binary tree too, or perfect binary tree, whatever the terminology is, because every node has two branches. Full binary tree, as we call it. Yeah, it's a full binary tree. Because if you notice, every node, even intermediate nodes, when it is branching out, it has two nodes. I'm just quickly verifying visually here. Yeah, it's a complete binary tree. We'll be covering those topics, by the way. So what I would do, I would probably go do a for loop from the root, go to its children, continue go to the children's children until there is no child, right? And traverse back. And when I'm traversing back, I would keep track of how much depth I went, right? So by following the branches, like I go from here, I'm showing the cursor here. I go, let's say from the root, I go here to the first one. Okay? I keep track of count. I say I went one deep. Then this one has no other child. So I come back up, it is one. I go to the right subtree. From there I go again. And one more. So I'll keep track of the count again. So like that I keep track of traversing all these things and counting, right? And whichever is the largest number that I get after traversing the entire tree, that tells me the depth of the tree. Okay? That is the easiest way to do it, right? Even to come up with an algorithm, typically we try to visualize something like that, by the way. Remember I told you last class, I said anything to do with linked lists and all that, I always draw up to three linked list nodes to flush out my algorithm. The moment I do three things, three nodes there, I can figure out the algorithm to 90% accuracy. The rest is hacking, of course, right? Same thing here. I traverse a few of these branches I can flush out the algorithm, but it seems to me that you traverse each of the branches and then you figure out the depth. Okay. Wait till I make you write in a program code for this. Okay. Couple of other terminology. I'll speed up now. If a path exists from node A to node B, A is called the ancestor of B and B is called the descendant of A. Okay. Ancestor, descendant. Very common English terms that you are familiar with. Okay. So in a way, what happens is if you look at all the intermediate nodes, a node is both an ancestor and a descendant of itself. It's a single node, right? So if you just say a path exists, yeah. If you have a node, in some context it is the ancestor of its children, but it's also a descendant of its parent. So it has two roles to play, ancestor and descendant. Okay? Now, to be precise, you can add what is known as a strict condition, okay? Meaning you are excluding equality. Okay? In that case, we say A is a strict descendant of B if A is a descendant of B, but not A not equal to B. That means there is some branch going from A to B. That is what the strict condition means. Okay? Here are some examples here. Still keeping it simple because, so that in the first one, picture there, if you see the descendants of node B, the one in blue, highlighted in blue, right? Where it's not a strict condition. You're saying B, C, E, D, F, G. You're going down, right? All the children, and all that. Okay? The ancestors of node I are H and A. Pretty straightforward, right? So here you are showing the same, that big science example that I took. It's showing all the descendants. Okay, mark all the descendants. That's how they mark it. Okay. Now, this is all great. Now, the same tree structure, now it gets a little bit more complicated. Even if you get lost while I'm explaining this, don't worry too much about it. We will when we get into implementation, your concepts will become much more clear. Okay? You can actually define a tree recursively. This is standard. I would call it like a mathematics-oriented definition. There's a nice book on graph theory by Nursing Dio. Faculty members, you probably know that. Very great man, Nursing Dio professor. Okay? He wrote a fantastic book, used worldwide. Okay? So this is how you define it. A degree 0 node is a tree, meaning there's only one node. A node with degree n is a tree if it has n children and all of its children are disjoint trees. Okay? They're disjoint because there is no intersection nodes. If you really look at it, what it boils down to, it's not a network. You will get unique paths. That is what this condition boils down to. Okay? Now, given any node A within a tree with root R, the collection of A and all of its descendants, is said to be a subtree of the tree with root A. So here you can see, if you see A, there is a subtree which is rooted in B, if you go to the left branch. That's called the left subtree. I'm introducing some terminology. Pay careful attention there. All tree traversal is based on left subtree, right subtree. So if you look at root A, the left of A, or at least visually what we are looking at, we call this, anything rooted in B here is called the left subtree. Okay? So given any node A within a tree with root R, the collection of A and all of its descendants is said to be a subtree of the tree with root A. So B is a subtree of root A. H is the subtree of root A. Correct? Now when you come down further, you say C. C is a subtree of B. And E is a subtree of B. Like that. So you have the concept of a root, you have descendants, you have ancestors, you have intermediate nodes, you have leaves, you have subtrees, you have depth, and you have degree. See how much terminology we introduced in the last, 40 minutes or so. Okay, so a lot of terminology there. Okay. The same thing, I'm going to talk about terminology in a slightly different way. Same thing, just to reiterate. Those are the concepts, but different, depending on which book you read. Those are the concepts, but okay, somebody mute yourself. I'm getting echo. Okay, somebody mute yourself. Did anyone put something in the chat? No. Okay, I'm getting echo. Please mute yourself. Echo. Please mute yourself. Let me see. JNTV, I'm muting you. I'm muting you. Yeah. I'm muting you. FCCW, I'm muting you. Okay, great. So, same thing, depending on which book you read and all, they kind of talk about these things in different ways, right? So, I'm giving a different spin for the terminology here before I let you do some exercise, okay? So, node. The node is the item of information plus the branches to each node, okay? Degree, the number of subtrees of a node, okay? See, we use the word degree elsewhere too, but slightly different perspective, right? The number of subtrees of a node is called the degree, okay? Degree of a tree is the maximum of the degree of the nodes in a tree. So if some subtree has degree 3 and some other subtree has degree 4, then the degree of the tree would be 4, okay? Terminal nodes, these are called the leaf nodes. So we have been using the term leaf, okay, whereas they call it terminal node. Now notice one thing here, the nodes, terminal nodes have degree 0, because, interesting definition of degree here, right, because you look at subtrees. This author defined it in terms of subtrees of a node. Leaf nodes have no subtrees, right, because they are terminal nodes. So their degree is 0. So if you are when you say, hey, the terminal node has degree 1, true or false, you should say false. Okay? Non-terminal nodes are the ones that don't belong to terminal nodes. Okay? Children. The roots of the subtrees of node X are the children of X. Okay? Remember the word keyword here, root. Okay? The roots of the subtrees of a node X are the children of X. Parent. X is the parent of its children. Okay? What do I do here? Okay. Sorry, let me put it in a presentation mode. Okay. Siblings. Children of the same parent are said to be siblings. Ancestors, we know that there is no difference in how it is defined here. The level of a node is defined by letting the root be at level 1. If a node is at level L, then its children are at level L plus 1. Notice how he is counting. The root is called level 1. Okay? Whether you call it level or depth, right? I remember earlier I called depth of the node, right? Whereas here the author is calling it level of a node. But they are one and the same, right? Conceptually. Now height of the tree. Even this I called it the depth of the tree. See, the terminology is, the terms are different, but the meaning is the same. So the maximum level of any node in the tree. Different nodes are different levels. Whatever is the max value of that will become the depth of the tree. Okay. Here is an example. Okay. Before we get into the example, take note of the property there. Very interesting property. When you do my advanced data structure class, we actually get into all these details. The property is, if you look at a tree, the number of edges is always equal to the number of nodes minus 1. I don't know if anyone noticed that so far in the presentation. Here the number of nodes are what? 1, 2, 3, 4, 5, 6, 7, 8, 9. If you look at the number of edges, there are 8 exactly. Okay. The property holds true and it can be proved. Okay. So in this picture here, you can see the A is the root node. And you can see parent of D and E is B. C is the sibling of B. D and D are children of B, blah, blah, blah. A, B, C, and H are internal nodes, you know that. The level of E is 3. And why do you see it's 3? Because you're considering root node as level 1. Okay. Now this is, I'm not too happy with that because for me, computer science, for me, number 0 is always finite start, right? So I don't know whether I would say level of E is 3. If I don't give you the numbers level 1, 2, 3, and 4 in a test, then if you say level of E is 2, I would call that the correct answer. Okay? Since the author has given level root A as level 1, then your answer should be 3 because 1, 2, and 3. E is the third level. Okay? You know what the ancestors are and you know what the descendants are. Okay? Any questions so far? Okay, no questions. Okay. Exercise time if there are no questions. That's it. I told you I'll just go slow this class. Just a few little concepts. So I did not put the full exercise here. I just put some things to get you going. So what I want you to do is work on multiple things here, okay? Groups of 2 again. To begin with, draw a family tree beginning with your great-grandfather, okay? Now, when you draw a tree, draw something interesting, okay? Say he is your great-grandfather, and your great-grandfather has at least, make sure there are at least 2 branches, okay? In good old days, they used to have so many children, like I remember one of my father's brother, he had 11 children. Okay? Don't draw 11 branches here. Your great-grandfather may have a cricket team full of kids. Draw about 2, 3 for illustration. That's why I call it for illustration only, right? Draw about 2 or 3 branches beginning with your great-grandfather. Let's say that means after great-grandfather, you will get your grandfather, right? Again, draw 2 or 3 from your grandfather to his children. Okay? One of them would be either your dad or mom. Okay? And then underneath that, you draw yourself along with your siblings. Okay? Now, if any of your siblings are married, if they have any children, take that branch and draw their children. Okay? So basically, you're drawing the tree going up to, let us say, 4 or 5 deep. And you don't have to go 4 or 5 deep for each and every node, okay? Just a few for illustration purposes. Okay? And once you draw that, list some ancestors, depth of the node that represents you in the tree. So at what level you are in the tree. Write that down. Okay? Is that the same as degree? Okay? What is your degree? I defined what a degree is, right? Degree shows how many branches go from you. Okay? And what is the height of the tree or the depth of the tree. Okay? Spend about 10 minutes on that. And we'll come back and discuss a few things and we are done. Okay? So, 10 minutes on this exercise. Now if you're done, draw for, let me be more precise, okay? After you're done with this, because I want you to get more practice, right? I'm creating this exercise on the, sorry, how do I go back here? Go back. Okay, then you draw a hierarchy of your college administration office. So make this 24. Okay, draw a hierarchy of your college administration office. Meaning like, I don't know whether you want to call it college or you want to call it JNTU. There's some interesting lessons that will come out of this particular one. Okay. So all of you know that JNTUK, let me be more precise, JNTUK. All of you know that there's a vice chancellor, right? I want you to draw a tree where the root of JNTUK is at the VC office. Okay? And from there, how would you draw the tree? Okay? I want you to go all the way to the department level, and department, underneath department, for the sake of argument, simply put another thing called branch, call it students. Okay? So students are at the leaf of the hierarchy. Whereas JNTU Kakinada Vice Chancellor is the root of the hierarchy. You understand the question? Do you understand the question? Give me feedback. Okay. Faculty members, please facilitate that. Let them do the first exercise for 10 minutes. That kind of gives them a comfort level. And then remaining time in the class, I want them to draw a hierarchy of the JNTUK administration office, where the root is the vice chancellor office, and then branches are, let me leave it there. Okay? So branches are, depending on, no, I cannot give you that hint. I just want you to draw the hierarchy because I want to see what kind of hierarchy different groups will come up with. There's a lot of interesting lessons that we can learn out of that. Okay? Great. Yeah, it's important for you to be interactive. I thought let me maybe sometimes, I think I should put up the slide again. Okay. See, learning is not the product of teaching, it's a product of activity. I follow that in each and every of my classes. By now you know that. Unless you do work, I cannot sleep well. I have to make you do some work in the classroom. Okay, ready, set, go. 11:23, 10 minutes for the first exercise. And the remaining time, let's call it another 15 minutes for that maybe, or 10 minutes. Then we'll wrap up in the last 5-10 minutes, okay? Remember, the more interaction you have, the more you learn. So, rule of thumb, the more you want to learn, the more you should interact. It's the dialogue which creates the knowledge. Okay, let me put the thing back. Sorry, I was sharing something and I'll go back to the exercise here. And after you draw, ask your faculty member or somebody take their help to put your image on the screen. You can take control of the screen and then you can what happened? I thought I shared my screen and I'm okay. Pretty easy class today, right? Comfortable pace. Second bullet, draw a hierarchy for JNTUK administration office where the root is the VC office somewhere sitting in Kakinada, and all of you are in different localities and all that. That will be a very interesting hierarchy to know. Generally, I see SVCW video, but today I am not seeing the video. Same thing with Pragati and Aditya, I am not seeing your videos. Okay, now JNTV is the... If you see me eating something, I apologize. It's my dinner at 11:35 p.m. in the night. So I'm assuming you're done with the first bullet here. Draw a family tree beginning with your great-grandfather. I'm assuming you all know what great-grandfather is, right? That is grandfather's father. The only video that I'm seeing is JNTV. Let me ask you a question. How many of you are doing the second bullet there? Raise your hands if you are working on the hierarchy of JNTUK administration. Raise your hand one more time. Okay, a few of you. Okay, good. I hope working on the family tree did not bring some emotions out. That was not the intent. Oh my God, my grandfather did not give me any inheritance. I'm so mad at it, right? I am. I know my grandfather was a very super rich guy, and what I got by the time I came was zero, absolutely zero. Give me a second, I have to take care of the dog. Okay, I turned on my audio now. Can you hear me or not? You should be able to hear me. Okay, you can hear you. Good. That's JNTV. Wow. Vice Chancellor, Rector, Registrar, Directorates, excellent. Continue, and then Vice Principal. Okay, where is JNTV in that? So in constituent colleges, is JNTUV constituent college? I believe it is, right? So you missed JNTUV there. Yeah, constituent colleges is a node, intermediate node, but within that I assume that you will put JNTUV as a college too, right, somewhere? So just an observation, okay? And then underneath that you have principal, vice principal, HODs, staff. And underneath staff you have students. Ultimately we want the department, right, and the students. Great. This is fantastic. This is what I mean by doing that interaction, right? I want each and every college to do that, like that, okay? Now, that is JNTUV. What about another college? What about other colleges who are there? What kind of a hierarchy you came up with? Does anybody wants to put that post up? That is good. Whoever did that, that is great. I'm looking at Aditya here, Bolisetti, Santoshi. I'm looking at SV, CW, Pragati. Pragati, Aditya, or SV, CW. Do you have anything to show like that? You can take control of the screen and then you can post your stuff. Now, JNTUV, let me ask you this. Which group came up with this hierarchy? Raise your hand. Who came up with this hierarchy? Is it the faculty member who came up with the hierarchy, or is it the student? See, nobody is raising their hand. That means the faculty member gave them the hierarchy, right? Somebody is smiling. Because students don't have any clue who a rector is. Okay, one of you, two of you. Okay. Rector is such a term that no one really knows what they really do. Okay, and then obviously not all students would have come with the same hierarchy, right? Unless by some magic you all know so well the organizational structure that it will all be the same for all of you. That never happens. In real life, that never happens. So that's the reason I'm asking other colleges to see what hierarchy they came up with. It so happens that in real life, you as programmers and as modelers of business processes, like business process modeling. So when you do your software engineering class, either from me or someone else, or database design class, you would learn a lot about modeling. These things come under the context of modeling. Okay? So you as a programmer, you are asked to, let's say, go to Cisco and develop something like a financial reporting system. And then the user would say, you know what, these are the different types of people that are there, and we need these types of access and all that. Then you start building hierarchies like that. Okay? Now when you do that, there is no right way or wrong way to come up with a hierarchy. So ultimately, who determines the hierarchy is the business user. You as a consultant is not determining the hierarchy. You are trying to capture what they are saying in terms of a picture like this. Then they go back to your picture and say, no, this is not how the hierarchy is. This is how I want you to change it, and so forth. Okay. So a hierarchy is a business-driven type of organization. Okay? So that's the reason why I said, hey, each one of you would probably come up with different types of answers for that. Now, it is also very important in terms of programming, in terms of coming up with the right algorithms to design the right hierarchy. Okay? If the hierarchy is poorly designed, it will have an immediate impact on performance of the system. Because ultimately you have to traverse the tree, remember? This is nothing but a tree, right? To get to the answer that you're looking for, depending on the type of query that you place on the system, If the hierarchy is not done correctly, it will take more time. Okay? So, the moral of the story is getting the hierarchy right is absolutely critical. And there is no one right way or wrong way. And whether the hierarchy is right or not is a business decision. It is not a technical decision. It's a business-driven decision. Okay? So to give you some idea about hierarchies, in Cisco, I worked on a project a long time ago, almost 10 years, 9 years ago maybe, where I was brought in to develop a security-driven model for a reporting system, a financial reporting system based on security. Okay? Who gets access to what data at what time? Okay, that's security. If you take my security class, I will go deep into that. So in the process of studying that, in order for me to implement that, when I probed it further, I realized in Cisco there are 50 plus types of hierarchies. 50 plus. There is an employee hierarchy, which starts from the CEO to Chief Operating Officer to different VPs, okay, different groups, functional groups, and so on. There's another hierarchy called job hierarchy. Okay, that's a job role hierarchy. So you have an engineer's job, you have an IT job, you have a operations job, which is different. Okay, so hierarchies are there everywhere. So in order for me to build a security model, I had to model it not only based on a job role hierarchy, but I also needed to model it based on a title hierarchy like CEO, VP, and so on. And like that, different hierarchies. Okay. So all those places, you would use a tree structure. Okay. That is the importance of a tree. Okay. All over, literally every single application that you develop would have some kind of a tree structure behind it. Okay, questions, comments? So I'm going to upload the slides. So we'll continue this conversation over the next, I would say at least 2 to 3 classes, where we'll go a little bit deep into trees. Okay? And even go beyond what your basic syllabus says. Okay. How did you do your internal exam? JNTV, I see a picture. Was the internal exam easy, tough, or somewhere in between? How many of you thought it was easy? Raise your hands. Nobody thought it was easy? Okay. How many of you thought it was very hard? Raise your hands. Nobody? Wow, it's neither tough nor easy. That means you already knew what the questions were and you were able to ace it. I don't know how you do your internals. Okay. See, the problem is if I give the test, I know exactly how my students are doing, right? But anyway, I hope you had a good thing, and I wanted to conclude today with a in the class JNTV I see, right? Hey guys, you should give big round of applause to all the women in your room. Okay? Let me see clapping hands for all the women in your room. You know why? Only 2 girls made India proud in Olympics. Right? Sindhu and the other one. So you should give a big round of applause to women. So go India and go women. Okay? So on that note, I'm done with my lecture today. Okay? Leaving you off a little bit sooner today. It's a good stopping point. I didn't want to get into some details of binary trees now. Okay? Great. If you have any questions, as always, you can reach out to me, send me an email. Email is faster than community. If you post a question in the community, your classmates would answer. If you send the email directly to me, I would answer. Okay. Let me post the slide deck now. I'll still be online for a few minutes.